Mouse, yes. Okay. Welcome learners. Today we shall discuss about the concept of graph isomorphism. You can recall the concepts which we have discussed in previous sessions like connectedness, walks, paths, cycles, diameter, complement. We shall see how these concepts are used to show graph isomorphism. So the term isomorphism is made of two Greek words, isos and morphe. The word isos means equal, the same, and morphe means shape or form. So the word isomorphism literally means equal form, that is equal shape. So in case of graph isomorphism, exactly it is the same situation. That means if we say that two graphs are isomorphic, they have the same form, they have the same structure, whether they are drawn differently or whether they are labeled differently. We shall explain in detail the concept and give plenty of examples, and then we shall come to the concept of self-complementary graphs. So before defining, let's look at these two graphs. At first glance, they might look quite different. As geometrical objects, these two graphs may look quite different, but we will show that they are essentially the same. We just transform the second graph, the graph on the right, and we will get a graph which will be similar to the one on the left. We just follow the movements. Okay, so now this is the graph. Now you can see that both these graphs look quite similar. They have the same structure. So now this is actually the process how to deform one graph into another form without changing the relationship between the vertices. We have not changed the relationship between any two vertices. If the vertices are adjacent, they are adjacent here as well, right? And if they are non-adjacent, they are non-adjacent here as well. So without affecting the relationship between any two vertices, if we can transform one graph into another, then those two graphs are isomorphic. Okay, so let's now define formally. Two simple graphs G and H are said to be isomorphic if there is a bijection F from the vertex set of G to the vertex set of H, such that whenever UV is an edge in G, FU, FV is an edge in H. That is, whenever two vertices U and V are adjacent in G, their images under F are adjacent in H. So to denote that two graphs are isomorphic, we shall use this symbol. We just read it, G is isomorphic to H, and when G and H are not isomorphic, we shall write this symbol. So it is read as G is not isomorphic to H. Okay, so let's look at some examples. Look at these two graphs. Both these graphs have 8 vertices and they have the same number of edges. You can count the number of edges, they are 12 edges. So they are they looking like the same graph? you just look at the vertices 1, 2, 3, 4 here, and the vertices V1, V2, V3, V4 here. If you just extract this cycle a little bit out, and then we can just deform it slightly, move the vertices to get the same graph as shown here. The only difference would be that these are labeled differently. Here the labels are 1, 2, 3, 4, and here the labels are V1, V2, V3 and so on. Okay, so these are isomorphic, but let's now find what the isomorphism is. So we just map the vertex the vertex 1 here to the vertex V1 here, and the vertex 2 to V2, 3 to V3, 4 to V4 and so on. That is, the vertex I here is mapped to the vertex Vi, and now you can check that this mapping is essentially an isomorphism. So to show a mapping which is an isomorphism, you have to first show that the mapping is a 1, 1 on 2. It is a bijection, right? So clearly it is a bijection because both have the same number of vertices, and we have mapped each vertex to here each vertex. Now look at this graph. It is a famous graph known as the Peterson graph. We shall draw an isomorphic copy of this graph. For convenience, we have just labeled we have just colored the vertices green and red. So let us just copy this on the right, and now we shall move the vertices here to get another graph which is an isomorphic copy of this graph without changing the adjacency relations. So just follow these movements. Okay, so we get this graph. We can see that how the vertices here, which were red and green, have moved to the vertices like this one. The red vertex, which is lying on the outer cycle here, now have reached to the central location, and its green neighbor, that is this vertex, has reached to this one, and its two green neighbors, which are here, they are these two vertices. Now an isomorphism is clear. You just map the red vertex to that red one, and its neighbor green one to this one, and so on. You can map all these vertices, and so that this mapping results in an isomorphism. So this is an isomorphic copy of the Peterson graph. In fact, there are several isomorphic copies, and these are just two. We just give one more copy, this one. You can show that these two graphs are isomorphic. You have to just find a 1, 1 on 2 mapping from the vertex set of this one to the vertex set of this. So first thing is that you can start any arbitrary labeling of the vertices here, and then you have to find a mapping. Okay, now let's look at some questions. If F is an isomorphism from a graph G to H, then show that F inverse is an isomorphism from H to G. This question is easy. You are given that F is an isomorphism from G to H, and you have to show that the inverse of F is an isomorphism from H to G. So since F is an isomorphism, F is a bijection, right? And therefore F inverse is also a bijection. Now only thing that remains is that you consider any two vertices in H, say U and V, which are adjacent, and then you have to show that the inverse, that the mappings, the images of the vertices U and V under F inverse are adjacent in G, which you can show easily. So we just leave it to you. Let's look at another question. So that the relation isomorphic to is an equivalence relation. It is clear that any graph is isomorphic to itself. So let's see, let's consider any three graphs G, H and K. So it is clear that G is isomorphic to G. Second, if G is isomorphic to H, then you can also see that you have just seen in the previous question H is isomorphic to G, right? Because if F is an isomorphism from G to H, then F inverse would be an isomorphism from H to G. And the third condition is if G is isomorphic to H and H is isomorphic to K, then G is isomorphic to K. This is called the transitivity. So it satisfies three conditions: reflexivity, symmetry and transitivity, and therefore the relation isomorphic to is an equivalence relation. Let's look at another question. Let G and H be two simple graphs which have equal orders and equal maximum degrees. The question is, must G be isomorphic to H? So what you have to show is, the answer is false. What you have to show is a counterexample. You have to just construct two graphs which have the same order and the same maximum degree, but they are not isomorphic. So one such pair of graphs is shown here. Just look at the graph G and H. Both have the same order. The 6 vertices are there and the same 6 vertices are also there. They have the same maximum degree. The maximum degree is 5 here and the maximum degree of H is also 5, right? But you can see that there is no vertex of degree 2 here, and there are 2 vertices of degree 2 here. So because an isomorphism maps a vertex of any degree k to a vertex of degree k only, right? It cannot map 2 vertices of different degrees. So this means that G and H are not isomorphic. Now there is another question. So there is a unique up to isomorphism 3 regular graph on 6 vertices. You have to check whether this statement is true or false. So what you have to do, you just construct all 3 regular graphs on 6 vertices and see whether they are isomorphic or not, whether you get any 2 different graphs, that means 2 different graphs which are not isomorphic. So you can do this yourself. You just try all the 3 regular graphs on 6 vertices and you will get the answer. Let's look at an important result in this regard. Let G and H be 2 isomorphic graphs. If G is connected, then so is H. That is, if G is connected, then H is also connected. We can prove it. We just give you an idea how to prove it. We are given that G and H are isomorphic, right? And G is connected. we have to show that H is connected. So we just pick any two vertices, say X and Y in H, and we'll show that X and Y are connected by a path in H. So geometrically, let's see, G and H are these two graphs, and F is an isomorphism from G to H. You just pick any two vertices here, X and Y. Since F is an isomorphism from G to H, there are pre-images of X and Y in G, and let's call these images, pre-images, U and V. That is, U maps to X and V maps to Y. Now G is connected, so U and V must be connected by some path, and using this path we shall get a path joining X and Y in H. So just you can specify the vertices on this path, say W0, W1, W2 and so on, where W0 is the first vertex U and W1 is the second vertex. So if W1 is adjacent here to U, then the image of W1 under F, that is F W1, would be adjacent to X, right, because F is an isomorphism. Similarly, W2 is adjacent to W1, so the image of W2, that is F W2, would be adjacent to F W1, right. In this way, this graph, the image of this path becomes a path, an XY path in H. Thus, if G is connected, then H is also connected. In fact, there is nothing special about connectedness. If G and H are isomorphic, then they share all the properties, right. That means if G has some property, then the same property is also possessed by H. For instance, G has maximum degree K, then H would also have the maximum degree K. If G is connected, H is also connected. If G has K components, H would also have the same K components. If G has any particular cycle or any particular path, H would also have that particular path or cycle. If G has any induced subgraph, H would also have that induced subgraph. That means whatever property G possesses, H would also possess the same property if G and H are isomorphic. Let's look at now this question. Are the following graphs isomorphic? It is clear that G is disconnected and H is connected, and hence G and H are not isomorphic. Now look at these two graphs. You can see that both G and H have the same number of vertices, that is, both have 8 vertices, and both have the same number of edges as well, right. There are 10 edges here and there are 10 edges here. You can see that the maximum degree of G is 3 and the maximum degree of H is also 3. The minimum degree of G is 2, the minimum degree of H is 2. And so, are they isomorphic? They have this here lot of properties. So let's look at some other properties. G has no triangle, right, and H also has no triangles. Let's look at cycles of length 4. Does G have any cycle of length 4? Yes, we can see that this is a cycle of length 4, a C4, right. Does H have any cycles of length 4? Of course H has. This is one such cycle, and this is not the only one. You can see that this is also a 4 cycle, and this one is also a 4 cycle. Now this gives us a clue that G and H are not isomorphic, because G has exactly one 4 cycle and H has 3 4 cycles, and therefore G and H are not isomorphic. Okay, now consider these two graphs G and H. We have to see whether they are isomorphic or not. You can recall that G is the famous gross graph. It has 11 vertices and 20 edges. The graph H also has 11 vertices and the same number of edges. The maximum degree of G is 5. The maximum degree of H is also 5. Both G and H are connected. The minimum degree of G is 2 and the minimum degree of H is 3. You can see that there is no vertex of degree 2 here. So this just shows that G and H are not isomorphic. We can also look at another property. For instance, just consider these two vertices, the central one, because they are the unique vertices. G has only one vertex of degree 5 and H also has this vertex which is of degree 5. So any isomorphism between G and H would map this vertex to this one, right? So that means if we remove these two vertices, the remaining subgraph should be isomorphic. But you can see that if you remove these two vertices, what you get is this one. This is an induced subgraph of G and this is an induced subgraph of H. This subgraph is regular of degree 3. All the vertices have degree 3 here, and all the here, but it is not regular. You can see that there are vertices of degree 4 as well as the vertices of degree 2. So this is also one way to show that G and H are not isomorphic. So showing them two graphs are not isomorphic, you can just pick any property which is possessed by one graph and not possessed by the other graph. However, if two graphs are isomorphic, then you have to specifically find an isomorphism between them. That is, that prove that function is an isomorphism. Let's now come to the relationship between complement and isomorphism. How is the complement of a graph related to the concept of isomorphism? You know that if two graphs have too many vertices, then their complement would have too few vertices. So this kind of relation is important in the sense of proving or disproving isomorphism between two graphs via their complements. So let's see what this theorem says. So let G and H be two simple graphs, then G is isomorphic to H if and only if G bar is isomorphic to H bar. That is, G and H are isomorphic if and only if their complements are isomorphic. So let's first prove this. So we shall assume that G and H are isomorphic and prove that G bar is isomorphic to H bar. So let G be isomorphic to H So there is an isomorphism from F from G to H. Then F is a bijection from Vg to Vh, right? And hence F is a bijection from Vg bar to Vh bar, because Vg bar is nothing but Vg and Vh bar is nothing but Vh. So now it remains to show that F is an isomorphism from G bar to H bar. So we just pick any edge UV in G bar and will show that the image of this edge under F is an edge in H bar. So UV in edge in G bar means that UV is not an edge in G, right? And you know that if any edge is missing in one graph G and G is isomorphic to H, then its image under F cannot be present in H as well, right? Otherwise it will be a contradiction. That is, so if UV doesn't belong to EG, then FV also doesn't belong to EH, and this means that FV belongs to EH bar. So thus we have proved that you take any edge in G bar, then its image is also an edge in H bar, that is G bar is isomorphic to H bar. Now we use the same argument on G bar isomorphic to H bar. We assume that G bar is isomorphic to H bar and will conclude that G is isomorphic to H. Okay, so G bar is isomorphic to H bar means the above argument implies that the complement of G bar is isomorphic to the complement of H bar, and which is nothing but G is isomorphic to H. So thus we have proved that two graphs are isomorphic, two simple graphs are isomorphic if and only if their complements are isomorphic. Now let's look at some questions. So just consider these two graphs G and H shown here. Are G and H isomorphic? You can see that there are too many edges in G and H. So let's draw their complements. The complements are shown here. G bar has just two edges, whereas H bar contains three edges. So this shows that G bar is not isomorphic to H bar, and therefore by the theorem we have just proved G is not isomorphic to H. So the theorem is quite important in the sense when you have two graphs which have quite many edges, then you can just draw their complements, and whatever conclusion you get about their complements, the same holds about the graphs as well. Okay, now we come to the concept of self-complementary graphs. It is quite possible that a graph may be isomorphic to its complement, and a self-complementary graph is nothing but such a graph. Formally, a simple graph G is said to be self-complementary if G is isomorphic to G bar. For instance, just consider this graph on four vertices V1, V2, V3, V4. It is actually a path on four vertices, that is P4. It has three edges. Now let's draw its complement. So this is the complement of P4. You can see that the edge V1, V3 is missing here, and therefore V1, V3 is present here. Likewise, V1, V4 is missing, so V1, V4 is present, and V2, V4 is missing, so V2, V4 is present. So this graph has complement this one. Do you find that these two graphs are isomorphic? Of course, they are isomorphic, because you can see, for instance, just map V1 to V2, V2 to V4, V3 to V1, and V4 to V3. This produces an isomorphism. You can just verify this. So therefore, P4 is self-complementary. Likewise, just consider the cycle C5. Its complement is this one. All the missing edges are present here, C5 bar, and if you just see, if you just transform it, you will get a C5. And in fact, finding an isomorphism also not difficult here. You can just map any vertex here to this one, and then start following how its neighbors are there. For instance, you just after mapping this vertex to this one, you can map this vertex to this one and this one to this one, right? And then these two vertices are mapped likewise to these vertices. So, and then you can check that all the edges which are present here have the same kind of relationship here. So C5 is also self-complementary. Now let's look at an important result about self-complementary graphs. It says that let G be an n vertex self-complementary graph, then n or n minus 1 is divisible by 4. To prove it, we are given that G is self-complementary, right? So this means that both G and G bar have the same number of edges, say m. Hence, if you just add the number of edges between G and G bar, what you get is the size of the complete graph on n vertices, that is 2m equals to n choose 2, which implies 2m equals to n into n minus 1 by 2, and now this implies 4m equals to n into n minus 1. So from here it is clear that either n or n minus 1 is a multiple of 4, right? That is, either n or n minus 1 is divisible by 4. So this is just a property of self-complement graph. However, the converse of this theorem is not true. That is, let G be any n vertex simple graph where n or n minus 1 is divisible by 4, then G need not be self-complementary, right? And you can construct a counterexample easily. Let's look at another question. Construct a self-complementary graph of order 8. So we just construct here. Look at this graph. It has 8 vertices, right? And now we shall draw all the missing edges here to get the complement of this. So these are all the missing edges, the red ones, and now we can extract this complement. So this gives us the complement. You can just find out an isomorphism from this one to this one. So this is a self-complementary graph on 8 vertices. Let's look at some more questions. Is the Peterson graph self-complementary? You just draw the Peterson graph and its complement. and see whether there is an isomorphism between them or not. Likewise, is the following graph self-complementary? Just draw its complement and check whether there is an isomorphism between this graph and its complement or not. Likewise, now we consider the last question. Given an example of 2 3 regular simple graphs that are not isomorphic but have the same order, the same size and the same number of components, and if such a pair does not exist, then you explain why no such pair exists. You can just think of 3 regular simple graphs on least number of vertices, and then you look at that whether those graphs satisfy these conditions or not. So we have discussed in this session the concept of graph isomorphism. We have seen a lot of examples and questions. We have seen how the concept of complement is related and is helpful in deciding whether 2 graphs are isomorphic or not. And finally, we have looked at the concept of self-complementary graphs and some properties of such graphs. So we end this session here.